with the transition.
Hello, everyone.
And thank you.
Hello, everyone. My name is Diego Perez. I have worked with Magopá and Esteban Meneses, and this will be the presentation of our paper called On the Detection of Silent Data Corruptions in HPC Applications Using Redundant Multithreading. Okay, so what is the problem? This is a current microchip. It's a complex system, and sometimes external causes such as sun radiation might impact the chip and cause a bit to flip, bit flips. So what that means is that the final result of a calculation might be totally wrong, might be corrupted, and the user can be completely unaware of this issue. That is a regular personal computer, but if we increase the scale and we move to a data center, this problem becomes more and more risky, more and more dangerous. So what is usually done to deal with this?
So I'm starting to get some chop.
One category of this approach is to replicate at the process level, to replicate the whole process of the application. And if the sibling processes have a difference in their outputs, that indicates a silent data corruption. This is a reliable technique, but it doubles the amount of resources required. So the data, the calculations, and the network communications. So that is a lot of overhead. So contrary to that, there is thread replication, in which the replication happens at the thread level, and it replicates the computations but not the data. So it's supposed to be cheaper, but because it does not replicate the data, it has to assume that the main memory is reliable. And the main technique within thread replication of this paper, the one that we focus on, it's called redundant multithreading, in which there are two threads that are used to detect silent data corruptions. Okay, so what are our contributions? We propose 3 improvements to redundant multithreading. And the first one is to use simultaneous multithreading for soft error detection. And there is 2 more of them that focus more on reducing the amount of data exchange. One is called variable aggregation and the other one is called selective checking. We have an evaluation in which we measure the trade-off of these improvements regarding performance versus reliability. And we show that for some HPC applications, the overhead can be as little as 1.1 times, which is quite desirable for a replication technique, while still providing a good error detection. Okay, so what is redundant multithreading in more detail? As I said, there are 2 threads used for error detection. One is called the leading thread and the other one is called the trailing thread. They can also be called producer thread and consumer. So this is what it looks like. The left one is the main thread, and these 2 are the leading and trailing thread. And they are practically the same with some differences. On the producer thread, or the leading thread, after every computation there would be a produce operation, and on the trailing thread, after every calculation, there will be a consume operation. The trailing thread will check if the value that it calculated and the value that it got from the producer are the same, and it's going to send a signal back to the leading thread informing that everything is okay. After that, the leading thread is allowed to continue. And because this is a thread level replication, this comparison needs to be made before this writes to memory. Okay, so something very important within redundant multithreading, it's what it's defined as a volatile memory access. A volatile memory is one that may be modified in ways unknown to the implementation. That means a variable that escapes the thread local scope. It pretty much means all those writes to memory. So in HPC applications, for example, an example would be all the MPI function calls, which are typically used in HPC applications. And a wrong execution on these operations can lead to a catastrophic and irreversible state. So we have to be sure that everything is okay before doing these risky operations, these volatile memory access points. So there are different communication patterns between the threads for redundant multithreading approaches. The first one is called synchronous, in which both threads execute synchronously. And these red dots exemplify the volatile points of the applications. These blue arrows represent the data that is being transferred between the threads. And as it can be seen here, in the synchronous approach, the leading thread is going to stop and wait after every calculation for a check of correctness from the trailing thread before continuing. So as it can be seen, there are a lot of waiting points. The leading thread will wait for after every calculation before continuing for a check of correctness, and the trailing thread might get to this point before the leading thread, so it has to wait for the data. So it's quite reliable, but it implies a lot of waiting points. So it's the worst regarding overhead. A totally opposite approach, it's called an asynchronous communication pattern, in which the data is still being sent and it will be verified for correctness, but the leading thread is not going to wait for that check of correctness. It's going to continue its execution. The trailing thread might detect that something is wrong, but the leading thread might have already done, especially at these volatile points, might have already done something irreversible. So especially for HPC applications that have a lot of these volatile access points, this is a risky approach. So regarding reliability, it's the worst, but regarding overhead, it's the best. And what is usually done is something in between, which is called a semi-synchronous communication pattern, in which the leading thread is only going to stop and wait at these volatile access points. And this is good regarding reliability and also regarding overhead. So this is the usual approach for a redundant multithreading approach. So as it can be seen, this inter-thread communication is a performance bottleneck. All the data that the threads need to be transferred implies a lot of overhead. Okay, so what are our contributions? We start with what we call vanilla redundant multithreading, which is a semi-synchronous approach that uses a single producer, single consumer queue in order to exchange the data between the threads. It's based on this reference, and it has a couple of optimizations regarding the queue that makes this suitable for this kind of a scenario. Our API includes 6 methods: produce and consume, the regular ones, produce and consume the volatile, and produce and consume direct, which are exemplified in the next figure. What we see at the left is the original code, at the center is the producer or leading, and at the right is the consumer or trailing thread code. What we see here at the left, it's a for loop that on each iteration it modifies a local variable. We see an MPI all reduce that takes this local variable and gathers the value in this global value, variable. This MPI all reduce is what would be identified as a volatile point. So in the vanilla approach, after every modification, there will be a produce operation on the leading thread, and there will be a consume check operation on the trailing thread. In these volatile points, there will be a produce volatile on the producer side, and there will be a consume volatile on the trailing thread. Something worth mentioning is that these volatile access points, or this MPI in this case, these instructions are not replicated. We do not want to send data twice to the neighbor or print something twice. We just want to make sure that everything is okay before continuing. So this consume produce volatile versions implies thread synchronization. The leading thread is going to stop and wait before executing this operation. And the produce and consume direct are just used to send data from one thread to the other one, because in the case of the consumer thread, this global variable value was not calculated. So it needs it in order to continue. Okay, so that is the vanilla redundant multithreaded approach. One of the optimizations that we propose is to leverage simultaneous multithreading. Hyperthreading, it's the Intel implementation of simultaneous multithreading, and what this means, what simultaneous multithreading means, is that a physical core, a single physical core, appears to have two or more logical cores. And this actually means that the core actually has more architectural state. These logical cores are just basically extra architectural state that allows two or more threads to be alive, to be ready to run at the same time. And well, sadly, not all HPC applications can benefit from hyperthreading or from SNT. So we propose to use these logical cores for error detection. And what we say is that if we pin the sibling replicated threads, the leading and the trailing threads, on these logical cores, they will share the L1 cache. And since they are sharing a lot of data, exchanging a lot of data, it makes sense to have this memory close. So instead of having a configuration like this one, in which there are multiple physical cores, the same color represents the pair of sibling replicated threads, and as it can be seen, each sibling is on a different core. This is here. Instead of having this, we propose to have the two sibling threads on the same physical core, to pin those threads in that physical core so that they share the L1 cache. This is at the hardware level. The other two optimizations proposed are more at the software level. The first one is called variable aggregation, and the purpose is to aggregate multiple values into one and use this aggregated value for error detection. Both threads will aggregate the same values. So it's kind of like this. Instead of sending and receiving a 3, a 7, a 14, and a 5, we will aggregate all these values into one and just send this 29. The trailing thread is going to aggregate the same values, and it will, or it should get to the same 29. So instead of sending all this data, we can just send a portion of it. And because of the aggregation operation, if a bit flip happens in any of these values, we will still be able to detect that something went wrong, because both threads should get to the same value. The other optimization that we propose, it's more strict than variable aggregation, and it's called selective checking. And the idea is to reduce the checks to a minimum, only at the volatile points. So as I said before, the volatile points are the points where a local variable might get published or published to main memory. So what we say is that if we remove these local checks and just focus on the volatile points, we can reduce significantly the amount of data exchanged. So we don't send these local changes, and we just make sure that everything is okay at the volatile points. So this reduces the performance significantly, but of course it poses some other questions regarding reliability that will be seen in the evaluation. Okay, so the evaluation. The first experiment, the goal is to measure the performance overhead of all these approaches, the vanilla, the aggregation, and the selective checking. For that, we chose two HPC applications that are representative of what the HPC community is doing. The first one is called COMD, which is a molecular dynamic simulation, and the other one is called HPCCG, which is a conjugate gradient. The node where we run this first performance experiment, it has two Intel Xeon. Each one of them has 10 physical cores, so there are 20 physical cores, and each physical core has 2 hyperthreads, so it's 40 threads in total. Okay, so what we see here is the normalized execution time for COMD. It's normalized execution time against the non-replicated version of the application. So this first bar, for example, it means that using the vanilla redundant multithreaded approach, it takes about 6.8 times more than the non-replicated execution. So that is a lot of time. That is a lot of overhead. These groups represent the level of optimization applied. Vanilla, it's no optimization. The second one is aggregation, and the third one is selective checking. And each one of these bars within each group represents whether we pin the sibling replicated threads to different cores or if we pin them to hyperthreads, to the same physical core. So as it can be seen, as we apply the next level of optimization, we are able to reduce more and more the performance overhead. And we can see that in all the cases, it is better to pin the threads to the hyperthreads, to pin the replicated sibling threads to hyperthreads. So in the case of COMD, we are able to reduce the overhead all the way from a 6.2 up to a 2.3. There's a big reduction. And in the case for HPCCG, we also see reduction as we increase the level of optimization applied. And we also see that in every case, using hyperthreads, it's the better idea, the best idea. So in this case, we are able to get to a 1.41 overhead, which is quite desirable for a replication technique. Okay, so what about the reliability of these techniques? How much errors are they able to detect? That is the next experiment. So in order to measure that, we have to inject soft errors. We have to inject, and we used a tool called Flipit, which is from Calum. The goal is to measure the soft error detection capabilities with all the optimizations. There is only one error injected per execution, and we have two experiments. One where we allowed errors only at the main kernel of the HPCCG app, which is a d-dot product between two vectors, and another one where we allow errors in all the HPCCG code. An error can be classified into 1 out of 5 states. If the error, if the application finishes with the expected result, we classify that error as benign. We know that it's injected, but if we take a look at the final result and it's the same as the expected one, we will consider that error to be benign. If the technique detects there is variation, we will classify that error as detected. If the application finishes correctly, but it finishes with a different result than the expected, we will classify that error as corrupted. If the application does not finish, if it crashes, that error is classified as crashed. And if the application does not finish, it's classified as a timeout. Okay, so this first table, it's where we allow errors only at the d-dot product, at the main kernel of this app. Something, well, we see each column is the level of optimization applied. And something worth mentioning is that, for example, with the non-replicated execution, we see about 66% of corrupted executions, which is quite high. We see about 30% of benign errors. That says that HPCCG is quite reliable. And if we take a look at the vanilla approach and the aggregation approach, we see that there are no corrupted executions, which is quite desirable. And this means that the error was able to detect pretty much all the errors that would have corrupted the final result. So that is why we see this high percentage of error detection. These two level of optimizations are able to detect all errors that would have corrupted the execution. But if we take a look at the selective checking optimization, we see that there is some percentage of corruption. So there is less detection, of course, and there is a bit of corruption. And this kind of exemplifies the trade-off between having the best performance overhead, but it has less reliability regarding detecting errors. If we allow errors to be injected in all the HPCCG code, we see something quite interesting. We see that HPCCG in general, for the non-replicated execution, it's quite robust. We see that 91% of the time the errors do not cause any harm. And something interesting is that the vanilla and the aggregation, they have less benign percentage of errors, but the reason for that is that actually they are detecting a lot of these benign errors. So these errors that are detected in these two cases would not have corrupted the final result, but still they are detected. And something quite interesting as well is that the selective checking approach also does not have any corrupted execution, which is quite desirable, and it detects some error detections. And we see again a high value of benign errors in the selective approach. But something very important is that it has no corrupted executions. Okay, so the conclusions. This paper studies redundant multithreaded to detect silent data corruptions in HPC applications. In order to improve performance, the first thing is to leverage SMT for error detections. And we also propose two techniques to reduce the data exchange between the threads: value aggregation and selective checking. We show that selective checking using simultaneous multithreading threads have a promising result with performance overhead as little as 1.41 times, while still ensuring a good error coverage. And for the future, we plan to study the impact of these optimizations in more detail on the probability of expecting a soft error, of experiencing a soft error, and we plan to study more applications. That is it. Thanks a lot. If you have any questions or comments, I will be happy to take them right now.
All right. And I believe the speaker was unable to join, but there's another speaker who's going to be answering questions, or is that a different paper?
No, I am here. I'm Diego.
Okay, all right.
Hello.
There you are. Okay, wasn't sure. Well, thank you for your talk and questions for Diego today. All right, here's one in the chat. What new processor features could you imagine that would support redundant multithreading natively without adding too much new logic? So hardware technologies that could be used.
Yeah, I know that at the start of this investigation, of this research, we took a look at another processor feature that was something like a transactional memory or something like that, that was able to correct or to classify a piece of code as, you could discard it and execute it again. But we tried it and it was not suitable for a redundant multithreading approach. I don't know what any other new processor features out there could be incorporated into this redundant multithreading approach right now. Yeah.
Okay. Looks like there's some additional typing. We'll give it a second here for those questions to come through. So you mentioned additional applications. That was my question. I was thinking about something that was non-iterative beside conjugate gradient. So I was curious if you guys have done any sort of preliminary stuff related to or others. I didn't know if you had in the paper discussed any other algorithms.
Yeah, those two applications are part of the Mantebo project, which is a set of mini apps. And we did take a look at other apps out there, which are also representative of HPC. But yeah, we didn't have a lot of time. We ran into some problems configuring Flipit and trying to understand what was really happening. So yeah, we definitely plan to do that for future work.
Okay, so I'm familiar with the Mentivo apps, but I also might suggest, so in the ECP project in the States, there's an entire effort on proxy applications or mini apps. Might be interesting to take a look at some of those too for portions of that. And I know there's overlap, but you might find that useful to look at. Looks like there's another question here. Would it be easy to use both value aggregation and selective checking, a mix of them, to have the trade-off that you want between overhead and error detection?
Well, the thing is that for those volatile points, you cannot send a portion of the data, or, I mean, when you get to that volatile points, to those MPI functional calls, you have to send all the data. So if you're aggregating values and you're at the middle of the aggregation granularity, you have to send as much as you have, because those instructions need the actual data and the complete data to perform well. But it might be interesting to see if I mean, yeah, in general, you could do that, but not for the volatile points. If you are sure to make, you have to be sure that at the volatile points you send the data, but for all the local operations, you could do this aggregation. So yeah, it could be interesting to study as well. I see that there's another question.
Yeah, about the injection of errors in your evaluation.
Yeah, we use Flipit. You can customize Flipit a lot. You can inject errors in arithmetic operations, in control operations, and in pointer instructions. We only choose to inject errors at the control operation and at the arithmetic operations, because when we allowed errors in pointers, we saw a lot of crashes, and that was not interesting. Yeah, well, that's part of the things you can customize in Flipit. Also, as we said, you can specify the parts of the code that you want errors to be injected in. In our case, for example, in order to have a consistency in error distribution, we chose only to inject errors at the user code. And what I mean by user code is like the original code of the application, not all the instructions added by the optimizations or by the redundant multithreaded technique, but just at the user code, so that it would be consistent amongst all the optimizations applied.
And he has a follow-up question about, in that way, about would you consider injecting at the message level? There's prior work at the level of MPI, so I think that's the input buffers.
I mean, we cannot inject errors in code that we don't have. I know that you could do some sort of tricky things to binary inject errors in those already compiled code, but yeah, the NPI function calls, what we did is just that we inject errors, or we allow errors in the parameters they take, not within the actual code of the MPI function calls.
Okay. And with the data values that you're injecting into, did you pay attention, I assume these are floating point things, about where in that bit stream, if there were high order portions or was it just random selection in those?
Yeah, that is also another thing that you can configure on Flipit. You can say in which bit of the selected register the error is going to be injected. And we chose, if I'm not mistaken, to leave that at a fixed point at the byte number 3 or something like that, so that we could see more errors, so that they would be more significant. I mean, to inject errors at the more significant bits, so that the errors manifest themselves. Yeah, we wanted to stress the techniques.
Excellent. All right. Well, thank you very much. A number of questions
You're
here. Any other questions for our speaker today? I'm not seeing any in the chat right now.
Right.
So thank you. Appreciate it.
You're welcome.
Good talk. All right. And so we're on time now for the transition here, which is a larger Q&A session that I think the organizers are gonna lead discussion here. I didn't know if we had a set of stock questions or how we wanted to proceed in that space. At this point, I think we can sort of try to mic on a few people and start that way, and also take questions in the chat. So, and these would be either questions for, you'd come up with from earlier talks in the day or our keynote, or items of general discussion in that. So let's open the floor.
Yeah, so this is Christian. Yeah, so this is basically just a session to open up the discussion to general questions or questions about the papers in detail. So I just read the reply by Thomas about the message level injection, and he's actually correct that the redundant multi-threading is sort of it goes back to the question of what are you protecting against? What is your, sometimes it's called sphere of replication or sphere of protection. And redundant multithreading typically protects against sort of errors within the processor. And when you basically inject errors at the MPI level, that would not be detected within the redundant multithreading. But it's sort of a good sort of leeway to basically discuss a little bit more about the types of failures we're seeing and the types of solutions we have. I have led a huge effort at Oak Ridge and at Argonne National Lab and at Lawrence Livermore National Lab about analyzing the failures and errors we're seeing on these large-scale systems. And we noticed that those change over time quite dramatically, and it's oftentimes unexpected problems we are facing because the manufacturers and integrators roughly have a good idea what they're expecting in these systems to fail, and they sort of plan that out, but oftentimes they make mistakes, or they certain things creep up on them that they didn't realize that would become problems. So these are then technology trends that sometimes appear that we thought we would be safe on that side, or we thought we would have protected ourselves against that. But in the end, we ran then into issues. So just to give a few examples here, one of our old Jaguar systems, which was something like 10 years or more than 10 years ago now, was designed basically from the ground up with not having a reliable network infrastructure, because it was the network architecture was 3D twisted torus, and having sort of the standard acknowledge-based system where you basically send a message, and then once the message is received, you send an acknowledge back, which basically means the sender needs to hold the message for a certain period of time, which basically means the message buffer is occupied for that period of time, and that in turn drastically reduces the injection rate of a compute node. So then the design decision was made then not to do that, but instead to focus on just using very reliable components to make this happening. And one aspect was that this particular system had the network interfaces as well as the routers on the compute node board itself. And the board also had multiple redundant power regulators. And it's something like a $1 or $2 part, one of these voltage regulators. And they were multiply redundant, I think 5 times redundant, and they blew out over time. So this cheap part over time basically blew out one after another. And we ended up having basically a board power failure once a month. And given that the rest of the system was not designed to be fault tolerant, that meant that basically once a month, we lost a router in a 3D twisted torus. And basically all applications would need to basically be killed immediately, and the entire system needed to be rebooted to reset the routes so that the system would route around that hole that's now in the 3D twisted torus. So this is sort of just an explanation of problems we have been facing in the past that we didn't anticipate because we thought we were basically mitigating against that, but in the end we didn't. Right. So I have lots of other stories about these kinds of things. I already mentioned the GPUs that were failing in the Titan computer that we also didn't really understood where that initially was coming from, and we also thought we mitigated against that. And at some point we had basically a failure rate of something like a GPU was failing every 2 hours in that system, which is basically makes the system almost impossible to use because it was designed for large scale computing jobs. And when I'm looking out into the future for the next 5 to 10 years, what I see is when we look at Intel, how Intel is struggling to get any new process technology to actually work. We have pretty much only one manufacturer left that is producing 7 and in the future 5 nanometer technology, process technology, and there will be reliability issues with that associated with that, and the manufacturers will try to mitigate against that, but there will be issues that they have not anticipated, especially longer term issues. If you run basically a computer longer than 3 years, you will run into longer term wear out issues that they have not anticipated that will become more problematic in the long term. So this was just a lead into this discussion, and I just open up the floor for anyone to basically offer comments, experiences, ask more questions about the papers we have, or general questions about resilience.
So I had a question from earlier in the day with the keynote. I think Peter's still with us here. And the
yes,
question,
I'm here, please.
Hi, Peter.
Hi.
So my question had to, when I heard what you were talking about, it's not so much a question as a comment or maybe thoughts you might have. It reminded me somewhat of the exascale computing project in the States, ECP, in the aspect that it was, you made a couple comments in there that, maybe this isn't sexy research, but this is, important work. And a lot of the same comments have been made and for parts of ECP where it's, a big effort and it's pieces that are needed. Is that an element? I'm unfamiliar with the EU structuring of things. Is there an element of that in this or anticipation in that avenue? Are you familiar with ECP?
So I actually think that Martin Schulz is well familiar with the US effort. He's one of the guys who was leading this effort on the European side. And I have to say that ECP is one of the projects that we were looking not only for the resilience aspect, but for all other things. Because typical comment, and this is maybe not related only to resilience, typical argument that we might have is that, yeah, Americans are so ahead of us because they have so much funding and we have much less funding. But again, it seems that many times we try to reinvent things that you already did. So this is something, definitely, we have to look towards you guys, and there's so many things to learn. And this is why there are some American authors This is why Christian is here, for example, is so you could help us and you could guide us.
Yeah. The part that struck me is that the notion that you have pieces of work that may need hardening or pushing forward to sort of bring them to state of practice was the element that sort of stood out to me. As in a lot of cases that's and it's not necessarily rewarded through publication immediately. It could be rewarded through software endeavors.
Yes,
So.
I mean, interesting. Something that maybe it's also, I mean, related to what Christian mentioned recently. It's that Intel has a lot of troubles to keep their systems reliable there, and I mean, we should not forget that we maybe have a slightly different road in Europe towards European exascale, towards European HPC. That was in some point it was betting on ARM. Now maybe it is betting on ARM and RISC-V. We are trying to do our own HPC processors. So we are trying to do them, like the version 0 of them. So it is sort of collaboration between our industry and our research. So everything is a bit messed up here, and it's maybe slightly different than US. This is why we were, or the rest of the world. This is why we were very explicit that our opinion is focused on European experience. But yes, there are a lot of challenges that we have to do here.
Peter, this is Stephen. Don't be discouraged. I think there's some philosophical differences between the US model and what I've seen in the past, a European model of doing things. We tend to spend a lot of money building the biggest for the sake of building the biggest. And quite frequently, not specifically in that area, but in general, my experience is the first to market or the first to build does not necessarily always win. So take a look at our failures and our struggles. And I think this is where Europe has succeeded and done some wonderful things in the past that I've followed in taking those and tuning them. So you don't have to spend as much money and build as many nodes necessarily as we do in the computer arms race and still be successful. So don't be discouraged at all. I think in some areas, in some ways, the approach that the European model in doing this stuff works wonderfully.
Thank you so much. I mean, and you're right. I mean, when you mention different models, which is maybe US versus European, and they are different models, and they can bring different things. So, and it's good that at least as part of this scientific community, we have this freedom to share ideas and to collaborate without thinking about NDAs so this is great opportunity. And I think there is opportunity also in Europe that some ideas come back to the industry, come back to the guys who will implement systems, and maybe they listen to us.
Well, and that's the great benefit of forums like this, that we can get together and openly share what we're working on. It's a little more difficult when, if it's a corporation that's doing it, they tend to hold that very closely as IP. But yet the research community, we can be more open with respect to that.
Yeah, something I also want to mention is while we are basically talking about HPC right now, the big systems, we also have to understand that there are other needs. So, for example, we're seeing the emergence of self-driving cars. These self-driving cars are basically self-driving GPU clusters. They're using GPUs to basically do all the real-time stuff to basically self-drive the car. And we will see other quote unquote self-driving things in the future. We are moving towards more intelligent systems where things like AI and so on will be deployed. There's one reason why we also included AI in the call for papers for this workshop. And for a lot of control problems, we will be facing, there are oftentimes real-time control problems, like a self-driving car, for example. And there are reliability problems there, right? So, and we need to figure out how to solve them. And the simplest answer right now is typically redundancy, right? But this may not be the best answer. So there are other opportunities here in the area of resilience as well, where we need to take a look at. So I just wanted to make sure that we throw this out as well, that our workshop is when we talk about high performance computing, we're not only talking about the big iron systems that sit at a few labs around the world. But
right, Christian, the resilience is cross-cutting through everything. The more we rely on our computing, the more our expectation is that it's going to come back with a correct result. If you recall early on, back when we were doing some what we called high availability computing, I recall the technology being picked up by one of the cell providers, and they actually put the redundancy and the reliability codes into their distributed switching fabric. And it was an area I hadn't thought of. And I remember they said something like, if they lost the capability to log their calls, they were losing millions of dollars in minutes. And so that became vitally important. So anywhere that we've come to rely on computing for an answer, even something as simple as looking at the weather, right? If you're looking at a satellite feed and you want to see if a storm's bearing down on you, if it's 15 minutes after the storm occurs that you get a response, that doesn't work. So it's cross-cutting more than just in high performance computing at this point.
Yeah, quite a number of weather centers are still deploying completely redundant systems. So that's another interesting piece, right? So, yeah, so there's a lot of interesting aspects here. I already pointed out this one paper that I'm, of course, a co-author on, the 3D coded summa paper that will be presented on Friday. What I like about this paper is it takes a little bit of a different approach to this problem. It takes it from an information theory kind of standpoint. And I think we need to start taking a look at that again. I mean, Shannon, right? So the great Shannon, he basically formulated all the information theory behind a lot of things we're looking at, right? But he was looking at this from a communication standpoint, and basically was arguing that all the we can basically send any type of information over any type of channel as long as we basically encode it correctly so that we can decode it reliably, right? So and I think there is an argument to be made for computation here as well, that we can come up with some more generalized concepts for reliable computation based on just information theory. So this may be actually some interesting future ideas where we can actually burn quite a few PhDs on. But yeah, so I wanted to make sure to mention that as well. Something else I also want to mention is that sometimes it's just the simple problems that occur at these big HPC systems. So with Summit, our current supercomputer that we used to be the #1 since June, it's not anymore #1. We basically had the problem that the system was engineered too close to the margins. What I mean by that is we had codes that were using the GPUs quite heavily, and we're using the GPUs at right at the boundary where between the automatic downclocking of the GPUs. So if you work with GPUs, you know that the GPUs are basically power gated. That means you can use them up to a certain amount. And then if you use them a little bit more, you basically run into the problem that the GPU produces way too much heat, it uses way too much power, and then automatically downclocks. And we had one scientific code that was basically running slightly below that margin, then slightly above that margin, then slightly below that margin, so that the power gating never engaged. And that apparently stressed out our power supplies for our compute nodes so much that the power supplies failed. Now we have redundant power supplies. So we had a power supply that failed. We had a failover to the redundant power supply. Then the failing power supply basically recovered and it would fail back to the, so we had a situation when the code was running that we had a constant fail over and fail back between the power supplies. And that failover and fail back itself wore out the power supplies over time. So this is sort of one of those things where then the reliability mechanism in it of itself wore out the system because there was just some under provisioning going on in the system. And we had to replace all 4,000 plus power, or 8,000 plus because they're redundant power supplies in that system. Right, so this is just another anecdote from one of these interesting things we see. Any other comments, any other questions? Feel free to ask questions in the chat as well.
So this is better from the BSc, and I would maybe like to throw something that we believe or not, but it is a comment that I have recently heard from various sides, is the Department of Energy or some people there consider that the resilience problem does not exist. And that funding that they are open to invest into this area is will be reduced. We have similar things in Europe, that although we have some European projects and all of them have this resilience label, essentially the effort dedicated to this is small or 0+. So do you think that, I mean, what is your opinion on this? Anybody, right? Anybody who is listening to this? Do you think that we should do something to convince people to do it different? And I don't know.
So this is Christian. Yeah, I can certainly attest to that. We have run into issues over the last several years that basically 5 years ago, a number of projects got funded in this area and was seen as an important project, important area to fund. The US Department of Energy even funded several manufacturers and integrators to look at resilience issues. This has sort of gone down significantly, and right now they're not interested in funding this. I see this part of the ups and downs of just the funding cycle, but also just the issue of communicating back to the funding agencies the problems that exist. And sometimes there are then conflicting interests as well. So I think in the end, the real data, the real experiences alone will convince funding agencies, right? So I mentioned before, we will have that paper at Supercomputing about the 11,000 GPUs we had to swap, right? So think about this. You basically have bought a supercomputer and you run it longer than expected. And suddenly you basically need to swap out more than half of the important components in the supercomputer for a price tag that is not public, but it's certainly in the millions of dollars, right? So this has been a severe impact on the operation on the system. The system itself, there were basically emails going out to people that were running large scale applications, and we told them, don't use the system. Yes, it's the largest scale system, one of the largest scale systems in the world, but you can't use it right now because it's constantly failing. And this certainly is getting communicated back to the funding agencies and so on, right? So this is important to make them also public, these experiences, right? There is sort of this interest by certain manufacturers and integrators that they want to get all the funding for fixing this problem. Or they're saying, you don't need to fund anybody else because we will provide the next system with more reliability features and so on, right? But I hope slowly the funding agencies realize that just relying on manufacturers or on integrators on any sort of promises is quite a futile effort, especially considering what's going on with Intel right now and what has been going on with Intel for the last several years. It's still unclear whether the Argonne HPC system will be actually the first US-based exascale system, or ours at Oak Ridge will be the first, because Intel is so far behind.
Well,
Right?
Christian,
Yeah.
just to jump in, one point that exacerbates this issue is that typically these machines that are going into the laboratories are machines of scale and size that the vendors have never built and never tested. And so for them to say it's going to be reliable, it's the equivalent of, I'll typically go into a class and say, how many people have ever really had a hardware failure on their notebook? And you'll maybe get 1 or 2 that raise their hand. And then if you put 100,000 of those machines together and start crunching on them, you're going to start to see a failure rate that exceeds those, those 2 machines. And so this is part of the problem, that the vendors are not building or constructing at the scale at which these machines are actually being implemented. Go ahead, Christian, I'm sorry.
Yeah, you're right. So this is one of the issues that I think there's also this attitude right now that certain manufacturers and integrators want to be sort of the big guy in the room that does everything for everybody, and they're then spectacularly failing on that.
Yeah, I mean, it would be great if they could, right? As a U.S. taxpayer, I would love to be able to have the machine purchased that fully works, but that doesn't happen. There's an enormous staff to put these machines together and make them actually work once a vendor drops it off the back of their truck.
Yeah. All right. Any other questions or comments in the last few minutes of this session? If not, Stephen, you want to close this out?
Yeah, I just want to jump in and say I posted on Slack my email and Christian's, and I would welcome folks that are interested in joining us next year in the 14th workshop. Hopefully, we will be invited back again next year to hold the 14th along with Europar again. I don't know that they've announced location yet. That may take place. Christian, do you know, do they have a location yet?
No, we don't even know. We will know in an hour probably, but
right. That's what I was thinking. I was thinking it would be announced at that point
on Friday at during the closing session.
Okay. And hopefully we'll be able to all meet in person at that point. If anyone has out of band questions or anything, feel free to contact any of us, myself, Christian, Thomas, or Farrell, and we'll be happy to talk about this. I will have my intro slides posted at least to our Resilience website. So if anyone wants some of those, they can access those there too. With that, I thank everyone for coming, and I guess we'll close the session then. Thank you very much.
Thank you.
Thanks, everyone.
Bye-bye.
Thanks. Bye-bye.
Bye.
Goodbye.